Hello everyone, welcome back to our Engineering Mechanics Dynamics class. Today we're going to solve our last problem of Newton's second law of motion, example 3. In this problem, from the picture you can see that we will be solving a problem that involves not a plane but the pilot itself. So what is if a plane takes a curved path, what is the normal vertical reaction by the seat onto the pilot, and we're going to solve that problem today. So let's see what is our learning objective. Solve a problem that deals with force and acceleration, of course, because we're going to use the Newton's second law of motion, and of course we're going to use cylindrical coordinate system. So in example 2, we're going to use Newton's second law of motion to determine a vertical reaction of the seat onto the pilot. So if any plane in the image you can see, if it takes a curved path, there is a tangential and normal force x. So we're going to use cylindrical coordinate to find out the vertical reaction of the seat onto the pilot. On the right image you can see this is actually my picture. When I was doing my study, I had the opportunity to fly F-16 Fighting Falcon demonstrator, so where I was able to take off and land. So it was fun. So we're gonna solve a problem of a plane, focusing on the pilot. So let's see the problem. A pilot of an airplane executes a vertical loop. So it's a vertical loop. It's important. So it's again in XY plane. Execute can be defined. So what it says basically is that the path you see here, the trajectory of the plane is making this loop like a flower loop, and it can be defined by this equation r 800 cos twice theta, while theta is in radian. If the pilot maintains a constant speed 100 feet per second, so here the speed of the pilot and the plane is 100 feet per second, determine the vertical reaction of the seat. So if someone is sitting here, his head is down because the plane is upside down. If he is sitting here and then flying the plane, so, and this is this could be his seat, right, where he's sitting. So what is the vertical reaction of the seat onto the pilot? So assume the pilot's weight is 165.35 pounds. So let's start solving the problem. Let's start with finding what is given. What are the knowns? The trajectory of the plane is known, r equals to 800 cos twice theta, and the velocity at that location A is 100 feet per second. Weight of the pilot 165.35 pound. What are the unknowns? The only unknown here is the question is asking what at the current position A shown in the figure, what is the normal vertical reaction? So when to solve, we need to know the vertical reaction at position A. So we know the radial direction. Since we are looking for the vertical reaction N, so we know there is r and theta, and since it's only making a vertical loop, so there we don't have to worry about the z coordinate. So first we're going to work with the r, so which is the radial distance of the plane from the center. So summation of force in r direction. So this is the distance r, and then the theta would be defined as from here, theta. So this is the origin, if we say. So then the angle is theta. So since we need the vertical reaction, so we're working on Fr, which is on the right side, mass into acceleration, and acceleration would be in radial acceleration. And we know from previous chapter, radial acceleration can be defined as r double dot, which is double derivative, second derivative of position r minus r into first derivative of theta whole square. So we need to find ar before we can solve the equation. So finding the derivatives. To find the ar, we need to find these derivatives here. So r is given 800 cos twice theta. If I take first derivative, for cos twice theta, it will give negative sine twice theta. That's why we have negative. And for chain of rule derivation, we have to take second derivative of twice theta, which will give us another 2. So if we take derivative of 2 theta, it will be 2. So that's multiplied by 800, so this is 1600, and we have the theta dot, because we're taking derivative with respect to we're taking derivative of r with respect to t, and now we're doing derivative of theta, so it's a different variable, so we have to have d theta dt, and which is represented as theta dot. Okay, so we need to find the second derivative, because we need this this r square. So if I take second derivative of the r1, I left with the 116, that's constant. So sine twice theta, theta dot. This is the second part I have to take derivative. So sine theta, it gives me 2 cos twice theta, and there is already theta dot, and then 2 cos twice theta, and then we have to take since the theta is not the derivative, like the same way we have here, we'll have another theta dot. So that theta dot and this previous theta dot gives you theta dot square. And then for the second part, so we did the derivative of this part only. And then for the second part, this part remains the same. And for theta dot, second derivative will be theta double dot. And everything is multiplied by the constant negative 600. Okay, so once we have r square, so we need theta dot. So how do we find the theta derivative? Because we had an equation for r, so we just took derivative, but how do we get theta dot? Because we don't have any theta equation. So we don't have a theta equation. So how do we take derivative of that? So we have to do a little trick. The velocity is given, right? 100 feet per second square. So velocity, the magnitude of the velocity is equals to the square root of here, the r component and theta component whole square. So we know VR, velocity of r in r direction, is the first derivative of r, and in current location we know the angle is 90 degree. So if we put here 90 degree, theta equals to 90 degree, that becomes 180 degree. So sine 180 degree is 0, so VR is 0. And V theta, we know it's r theta dot. This is how we get V theta. So r at 90 degrees, so if I put theta equals to 90 degree here, so cos 180 degree is negative 1, that gives me negative 800, and the theta dot remains the same because we're looking for theta dot. So if we plug this one 0 and V theta negative 800 theta dot here, so it will be whole square. If we solve it, and if we put here V equals to 100, we will get theta dot equals to 0.125 radian per second, because theta is defined as radian. So we found theta dot, we find r theta double dot and r dot. So now we can move to solving the problem. At position theta equals to 90, because this is the current position, r double dot, what is the value? We already have the equation for r double dot. We'll just plug the value. So theta equals to 90, there was 2 theta, so it will be 180 and 180 here. So if we plug the value, cos 180 negative 1 and sine 180 is 0, so finally we get r double dot equals to 50 feet per second square. So we go back to the equation of AR, acceleration in radial direction. We plug the value, r double dot equals to 50 and r equals to negative 800 at theta equals to 90. And theta dot we found 0.125, so that is whole square. So if we solve it, the radial acceleration in radial direction is 62.5 feet per second square. So we have solved AR. Now we are ready to solve the equation of motion. AR equals to MAR. So summation of force in radial direction, mass into acceleration into r. So let's do that. We plug the value. Summation of force in radial direction is the, if we see the image, there is two force. One is the normal or vertical reaction of the seat towards the pilot, which is defined by color green color arrow, and there is also the weight of the pilot itself. So there is two force acting in radial r direction. So negative n because it's downward, and the weight is also downward, so negative 165. Mass is the 165 pound divided by 32.2, that gives us the slug. And acceleration AR we just found 62.5, so we plug it there. So if we solve for n, we have only one unknown. We found that the n is negative 486.3 pounds. So the pilot at this position at A is feeling a force of negative 486.3 in this direction. This is the vertical reaction from the seat towards the of the pilot. So we have found n. So this is our answer. So next class, we're going to start new chapter 14. Till then, thank you so much. See you in class. And if you have any question about any lectures or any problem, just make a comment on the video and I'll try to explain that. Well, till then, thank you.